How you doing today? Today we are in chapter 6 of volume 1 of the 8th edition of wastewater treatment. And we're going to talk about trickling filters today. We call those fixed film versus what we call suspended growth and activated sludge. So suspended growth is what it is. It's suspended by the air that is supplied through blowers, whether that be positive displacement or centrifugal or turbo blowers. The role of aerobic microorganisms in wastewater treatment was recognized in 1890, and since then we've tried to develop these microorganisms so that we can treat the water so that we can discharge it to the surface waters. On the bottom of page 466, trickling filters, also called biofilters or biotowers, are centrifugal, rectangular, or square bioreactors filled with a media made of a natural or plastic material. The term filter is somewhat misleading as no straining action or physical filtration is taking place in the reactor. When we talk about a trickling filter, we talk about a round or square tank. The bottom is open, and it is filled with media, whether that be synthetic media or rock media. And we add the influent up to the top, and as the influent drops through the rocks, the media or the rocks have a bacteria slime growth on those. And as the water picks up air, as it jets through the rocks, that slime or growth then treats the wastewater. And so it's not something that is submerged, but think of it as a 5 gallon bucket with rocks in it. And you're adding influent or on top of it. And as it's going through the rocks, it is the organic matter is being consumed. This was a way for early wastewater treatment plants to efficiently treat wastewater without a lot of technology. The trickling filters on 467 are designed for a continuous flow of water and air, and there's no need for backwashing. So we call them filters, but we're not actually removing any of the solids. What we're doing is we're treating the BOD and the ammonia in that filter, and so it's not filtering out the solids. We remove the solids in the primary tank or some other process before we add it. So mainly we are trying to consume that organic matter. On the top of 469, you can see a picture of that. I believe that is a rock media trickling filter. And so the sprinklers are around the top, as you can see, and it runs in a circular motion. And so it sprinkles the influent on top of the rocks and then percolates down to the underdrain. The same thing you have on a plastic media filter. So you can use rocks or you can use a synthetic meter. On the um, on the page 468 is your standard activated sludge, but of course we're talking about um, fixed media. Rock media on page 471. Trickling filters were originally designed with media that consisted of natural material contained in the concrete structures. Rocks were commonly used, but redwood or treated wood slats were used in some structures. Rock media is rarely installed today. Trickling filters, this is on the bottom, Using rock media are shallow because the rocks are heavy and can crush other trickling filter components, such as the underdrain. So with rock trickling filters, we could only go so deep or so high because the rocks would actually crush the underdrain. So they came up with plastic medium. In the 1950s, you can see the different honeycomb shape plastic media and can be as high as 40 feet. So technology advanced with the trickling filters. There are more pictures on 475. There 476, there are two basic types of distribution nozzles. They're fixed and the rotary type. So there it's fixed, it does not move, and this is a rotary type. And you can see on page 477, that's actually pushed by the hydraulic flow to it. So it propels it in a circular motion, which distributes the influent um, universally across all the medium. The underdrain system. The underdrain system is the area between the concrete slab and the bottom of the media, called the underdrain system. It supports the media, collects the treated wastewater, and creates a plenum that allows air circulation throughout the media. We want that air circulation because the bugs, once again, that are on the media is what it needs: air plus that constant water with what we call organic or, food loading. Secondary clarifier. The overall performance of the trickling filter process is dependent on the ability of the secondary clarifier to separate the suspended solids from the treated wastewater. And so, whether our secondary clarifier is after, we want to be able, because sometimes it'll slough off, we want to be able, some of the solids will slough off the trickling filter. We want to be able to separate those solids from the system. Once again, I'll highlight on 485, no more than 1 to 2 foot sludge blanket should be maintained in a secondary clarifier. Under process controls, the contact on 487, the contact between the bacteria and the food is also affected by the flow. The higher the flow leads to shorter detention time and vice versa. Lower detention time can lead to lower pollutant removal rates. This is one of the reasons why recycling of the treated water back to the process can be used to offer another opportunity for the bacteria to feed on the pollutants. You have the influent coming in, it goes down our trickling filter. Some of that is sent off to the next stage, but some of that is recycled back to the head and then pushed over again over top of the trickling filter. And it's just an added efficiency. It's kind of like running the cake through the oven or taking half of the bacon and running it back through the skillet. We're just trying to increase the efficiency of our pollutant removal. And so you do have a recirculation rate in trickling filters. Hydraulic loading rate, we've talked about this, also called surface loading rate on page 490, is defined as the total amount of water supplied to the system per day in relation to the square feet occupied by the media present in the trickling filter. And so when you are operating a trickling filter, you need to know what your engineer designed it for. What is the hydraulic loading rate? Um, did they adequately take into consideration a recirculation ratio? Dosing rate on 493 is affected by the rotational speed of the trickling rate. The dosing rate of a trickling filter operated at a specific and unchanged hydraulic loading will double when the rotation speed of the arms is slowed by half. The dosing rate of the same trickling filter will be reduced by half when the rotation speed of the arms is double. So, when we speed it up, that it'll reduce it in half, the actual flow. So how fast it's going around will depend on the hydraulic loading rate. Recirculation of treated wastewater to the trickling filter is probably the most important parameter used to effectively control trickling filter process. One of the reasons recirculation is done is to dilute toxic waste. It's to reduce fly and snails, and diluting wastewater to reduce the strength of the wastewater being applied to the filter. It also prevents the filters from drying out. And so, once again, we want to pay attention to our recirculation rate. The main goal of a trickling filter is to remove BOD or TSS, um, or convert ammonia to nitrate and sometimes nitrogen gas. The overall performance of the process can and therefore be assessed by monitoring the removal of the efficiencies of each key parameter. So, we want to measure the effluent of our trickling filter, what comes out of it. We want to test it for ammonia. We want to test it for BOD, because how are we going to know how well it's operating unless we test it? And so knowing your influent BOD, your organic loading rate, and knowing the end result could tell you if you need to increase recirculation rate, or perhaps your filter is not working as it should. On page 499, you can see the different ways that between summer and air that it changes the natural ventilation. We want our filter to naturally have ventilation because microorganisms take that air and use that in its system. Let's talk about sampling and analysis on page 501. Grab samples are those samples that we take. If I went to my sink, opened up the tap, and took a sample, and then ran it for pH and DO. A composite sample is if I took a sample every hour for 24 hours out of my sink while the sink was flowing, and that is a composite sample. So when we talk about sampling, we want to know the different types of sampling that we have. Obviously, you may grab a sample from a trickling filter and it may be good on ammonia, but maybe it's during the afternoon where flows are low. And so to really know what our trickling filter is doing, we need to take a composite sample. And that sample needs to be throughout the journey of that trickling filter. On page 503, the presence of high TSS concentration in the final effluent is a sign of poor process performance. So you'll have heavy sloughing from the filters. You'll have a high hydraulic loading or short circuiting through the secondary. You could probably have shock loading caused by toxic waste or hydraulic or organic overloads. So we want to monitor our our effluent from your trickling filter. Let's talk about the 5 BOD. So when we talk about 5 BOD, it's just measuring the amount of biodegradable organic matter that is consumed by bacteria within 5 days. Um, the 5 day BOD is not a test that is good for daily processing because it does take 5 days. So when we talk about BOD, we want to see what what that bacteria in that water once it's going to the river or to another process. We want to see how much oxygen is it going to deplete in 5 days. So when we discharge it to the river, we want to know, is it going to deplete at the fifth or third or fourth day? How much oxygen are we going to do damage downstream? And not we're really looking for the organic matter. We're not looking for the ammonia. So we're looking at the carbaceous oxygen depletion and not the ammonia. Ammonia will cause oxygen depletion. Dissolved oxygen, when we talk about dissolved oxygen, we're just talking about how much oxygen is in the water. Clarity, we can do that just visually looking at the clarity. Um, we need to measure the pH because bacteria is known to be sensitive to pH. On the bottom of page 505, nutrients. Trickling filter bacteria need an adequate supply of nutrients to grow and properly treat wastewater. And I believe this is a test. But a test question. It is important to monitor the concentration amount of ammonium nitrate and orthophosphate and make sure that there's at least 5 pounds of ammonia nitrogen in 1 pound of orthophosphate for each 100 pounds of BOD supplied to the system. Nutrients will be added if the wastewater does not contain um, enough of it. So we have different filter classifications. Low rate on page 508. Low rate trickling filters are relatively simple treatment units, normally produce a constant effluent quality, even with varying influence. They can operate at organic loading rates less than 25 pounds of BOD per day. So when I'm talking about the difference between a low rate and intermediate rate and high, I'm really talking about their organic loading rate. And, you know, low rate is about 25 pounds per day. And intermediate, as you can see on page 509, is more around 40 pounds of BOD per day. So it can take a little bit more. High rate, we're up to 40 to 100 pounds of BOD. Um, High rate trickling filters that use plastic media require that a relatively high hydraulic loading rate be applied to the surface to keep the media wet and ensure a uniform contact. Roughing filters. We do a rough job, right? So filters are generally designed to allow a substantial amount of soluble BOD to go through. Nitrification and trickling filters. On page 511, it is important that enough alkalinity be present in the incoming water to maintain a pH of 6.5 to 8. Significant decrease in performance has been recorded as temperatures lower than 50 degrees. Therefore, the operator's strategy often has to be modified from season to season. This can consist of increasing the recirculation rate or operating more trickling filters. So sometimes, if it's freezing out or the temperature um, is colder, you might have to stop your recirculation rate so that it doesn't freeze. Or if your biological activity is decreasing, you would increase your circulation rate, because as you increase your circulation rate, you are increasing the performance of it. Um, in view of the higher level of control required to achieve uh, nitrification in a trickle filter, separating the nitrification from the BOD removal can be efficient. You can run on page 512, you can run trickling filters in parallel, and you can also run those in series. Um, Depending on what you're trying to do and the strategy that you're trying to complete. Ponding. So a lot of times we'll have ponding on page 524. Ponding and trickling filter ponding refers to the presence of ponds of water on the surface of the media. It is caused by a lack of drainage due to clogged voids. Um, one reason we can have that is excessive growth of insects and accumulation of fibers or trash in filters voids due to poor preliminary primary treatment. We don't want ponding. We want it to cascade through. And so if you're getting ponding, maybe your clarifier is not doing it, or your whatever your treatment upstream is maybe not doing a good job of removing some of that trash or fibers, or maybe you have an excessive growth of insects or snails. So ponding can be due to that. When we talk about um, filter flies on the bottom of 525, it says flooding of the filters with a saline or alkaline solution in addition to backwashing have been used to further abate filter flies. Chemical treatments are often used to address snail problems. Um, so sometimes you have to increase the hydraulic or the dosing rate to get rid of snails and filter media flies. Icing. Operation of trickling filters can be challenging in colder climates, so you have to decrease the recirculation rate, because as the water comes in, it's warmer from the collection system, and so decreasing that recirculation rate is paramount. On page 529, the rotating biological contactor. It's very similar to a trickling filter in that wastewater is treated by bacteria that is attached to media. The main difference between RBC and a trickling filter is that the RBC is not stationary. So we need to look at a picture of an RBC. So on page 6, you have your primary clarifier and then your RBC trains. Those go in a circle, and as the water passes through those, all of those stage 1, stage 2, it goes in a circle. So as those filter medias pick up the water and then come out of the water, you're getting your attached growth, you're getting oxygen on those actual media that's constantly going in and out of the water. So that trough is half full, the media is going in the water, coming back out, going in, and that's feeding the microorganisms with air, but is also treating the wastewater as it flows through. So the concept's the same, but the footprint and the layout is a little bit different. You can see a huge RBC there on page 533. The drive mechanisms used to rotate RBC shafts are either mechanically or air drive uh, units. So to rotate those, to make those spin, they can be either mechanical, or they can be diffused air to rotate those. that is the end of how much I'm going into chapter six. I may do another lesson on the integrated fixed film activated sludge process for another day. Thank you.